Hello friends, today I'll start with the counter. Okay, counter is the one of the part of the flip-flops. Flip-flop means normally if we consider about the D flip-flop, D flip-flop is used to store the only one binary bit. Okay, so but for counter we can store the multiple number of bits by using the counter. Or if we want to give the practical example, counter which counts the number of sequence. Okay, which counts the number of sequence and which can store the multiple number of bits by using the counter. If we apply the clock, it counts the number of sequence. How many sequence? Suppose 0, 1, 2, 3, like any sequence also it can count. It can also count the random sequence. Suppose 0, 5, 3, 2, like this way it can count, right? So and there are different numbers of counter, 0 to 5 counter, which counts the number from 0 to 5, like 0 to 9, like this way. So but for that, how we can design, it depends on the flip-flop and clocks, how we are giving the clocks and how we are connecting the flip-flops. Okay, so here two different kinds of the counters are there. Counter, okay, counter which counts number of sequence. Okay, two different counters are there. One is the asynchronous, another is the synchronous counter. Okay, in asynchronous counter, suppose you are designing one flip flop which has the one counter which has the two flip flops. Okay, so you are giving the two different clock pulse in two flip flops in case of the asynchronous counter, but in case of the synchronous counter, you are giving the same clock pulse to every flip flops in case of the synchronous counter. Okay, suppose here two flip flops. Suppose you are designing one counter, you have the two flip flops. So in asynchronous counter, you are giving one clock in first flip flop. Okay, and output of the first flip flop is connecting as a clock for second flip flop, clock 1 and clock 2. Okay, but in case of the synchronous counter, suppose you have the two flip flops, right? So you are giving the one single clock pulse to each flip flop. Okay, so at a time both the flip flop will work in case of the synchronous counter, but in case of the asynchronous counter, at a time both the flip flop will not work. Depends on this counter it will work, and depends on the output of the first flip flop, the second flip flop will work. Okay, so this is the asynchronous counter and this is the synchronous counter. Normally this synchronous counter is preferable because it is the first process as compared to the asynchronous counter, because it will be a slow process. First this flip flop will activated, after that this flip flop will activated like this way. But in case of the synchronous counter, at a time all the flip flop will activated, and based on this all the flip flop will get the output in case of the synchronous counter. Okay, now here so how can you design the synchronous counter? Okay, how many flip flops are required to design a particular counter, that I'll discuss now. Okay, so here synchronous counter. From the synchronous counter, so there are two types. One is the up counter and is the down counter. Okay, up counter which counts the number from 0 to suppose n minus 1, and down counter which counts the number from n minus 1 to 0. Okay, so suppose you have the suppose mod n counter. Okay, you want to design the mod n counter. So for that, how many number of flip flops are required? So n should be less than equal to 2 to the power capital N, where 2 to the small n, where n is the number of flip flop. Okay, and how many states are there? If you want to design mod n counter, how many states are there? 0 to n minus 1 states are there. So modern counter counts the number from 0 to n minus 1. Okay, if you have the n, if you have the capital N value, so the capital N should be less than equal to the power small n. Okay, so here in n is the number of flip flop. Okay, suppose you want to design the mod 8 counter. That means it counts the number from 0 to 8 minus 1, that means 0 to 7. Okay, right? So 8 should be less than is equal to 2 to the power small n. So that means 8 should be less than is equal to 2 to the power 3. So n is equal to 3. The total 3 number of flip-flops are required. Okay, so in this way you can calculate. Suppose mod 7. Okay, so 7 should be less than is equal to 2 to the power small n. Okay, in this way, so that for the mod 8 and mod 7, same number of flip-flops are required, but it counts the number from 0 to 6. Okay, mod 8 counts the number from 0 to 7, mod 7 is counts the number from 0 to 6. Okay, so now how is first question I will, so you can design all the counters, mod 8, mod 7, mod 5 and every counter. So if mod number is there, you can calculate the number of flip-flops, how many flip-flops are required for that particular purpose, right? So here I will now discuss the how can you design the mod 8 counter by using the T flip-flop. Okay, you can design any counter by using any flip-flop, T flip-flop, D flip-flop, JK flip-flop and SR flip-flop. Okay, so how can you design the mod 8 counter using T flip-flop, that I will discuss now. Okay, so here you can see in the mod 8 counter, in the mod 8 counter you can see total 0 to 7 number of states are required. Okay, total 0 to 7 number of states are required. For that, how many flip-flops are required? 3 number of flip-flops are required. Okay, so this you try to remember. I will discuss now. Synchronous mod 8 up counter. Okay, so I am discussing only the up counter. The down counter means the processor almost same, but number of sequence should be different for case of the down counter, because if the mod 8 down counter means it will be count the number from 7 to 0, 7, 6, 5, 4, like this way. And mod 8 counter, up counter, it counts the number from 0 to 7. Okay, right? So mod 8 up counter using T flip-flop. Okay, so mod 8 means how many states are there? 0 to 7 states. First I am writing. So if you design the T flip-flop, first here I am writing the acceleration table of T flip-flop. Okay, so if this is the acceleration table Qn plus 1. Okay, and T. Okay, so if you try to remember the acceleration table, it will be like this way. Present state, both state, present state and previous state both are same when your t is 0. Both are opposite when your t is 1. This is the acceleration table for T flip-flop. Now I am writing the present state for mod 8 counter and next state for mod 8 counter. Okay, so mod 8 means it counts the number from 0 to 7. 7 should be less than is equal to 2 to the power n, that means your n is equal to 3. Okay, so 3 number of flip-flops are required. So that means your present state should contain the 3 outputs and your next state should contain the 3 outputs. Okay, so suppose Q2, Q1, Q0, Q2 plus, Q1 plus and Q0 plus. Present state, next state, or past state or present state, like this way. Okay, so in the present state I will write the number from 0 to 7. Okay, 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0. Okay, in case of the next step, so what is the, if the number, normally this is the binary number 0 1 2 3 4 5 6 7. Okay, so what is the counter? Counter counts the number from 0 to 7. Okay, if 0 is the present state, after the 0, which number will come? 1 will come, right? After the 0, which number will come? 1 will come. Okay, that means here it will be 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So for 7 again it will come to the 0. For 7 again it will come to the 0. Okay, so 1 1 0 1 1 1 is the 0 0 0, right? 0 0 0. So if 0 is the present state, 1 is the next state, like this. If 7 is the present state, again after the 7 and 0 will come. 0 will be the next state. Okay, right? Now I am writing the acceleration table for this corresponding present state and the next state. Okay, this will be T2, T1 and T0. Okay, so for T2, which is the present state, Q2 and Q2 plus is the present state and the next state. Okay, so I have to follow this acceleration table for writing T2, T1 and T0. Right, so here you can see in the first three cases, okay, all three are 0. Okay, so if 0 0 means T2 will be 0 0 0, first three cases, 0 0 0 0 0 0, it is 0 0 0, 0 0 means 0. Okay, now fourth one is the 0 1. Fourth one is the 0 1. 0 1 means it is 1. Okay, the 1 1. 1 1 means again 0. This is also 1 1 means 1 and 1. 1 1 means again 0. 1 1 means again 0. This is 1 0. 1 0 means it is 1. Okay, now come to the T1. In T1 it is 0 0. 0 0 means 0. 0 1 means 1. It's like to XOR operation. Okay, then 1 1 means 0. Okay, 1 0 means 1. Okay, then 0 0 0 0 means 0. 0 1 0 1 means 1. 1 1 1 1 means 0. 1 0 1 0 means again it is 1. Okay, for last answer T is not. T not, you can see 0 1 1 0 0 1 1 0 like this way. So all will be 1. No same numbers are there. 0 1, that means 1. Again 1 0 1 0, it is 0 1 like this one. So all are 1. Okay, right? So I have written the T2, T1, T0. Now I have to design the mod it counter. For that, okay, so I have to do the K map for T2, T1 and T0. So for T2, T1 and 0, this present state Q2, Q1, K0, this will be acted as a inputs for T2, T1, T0. So T2, T1, T0, these three are my three different outputs. So I have to write the KMF for T2, T1, T0 by considering Q2, Q1, K0 as a inputs. Okay. So first I am doing the for T1. Sorry, T2. Okay. T2. Right. So here it is Q2, here it is Q1 and I think it is busy one, Q1 and Q0. Okay. So I am just checking. You know it is 0, 1, 2, 3, 4, 5, 6, 7. 0, 0, 0, 1, 1, 1, 0. Okay. So 42 is 1 for which combination? 3, 0, 1, 1. Okay. 3 combinations. Here my T2 is 1 and on the last 7. Here my T2 is 1. So that means for other cases my T2 is 0. Okay, so this I can do one pair. What will be the T2? T2 will be the Q1, Q naught. Okay, got it? Just I am doing the simple chemical for these three outputs and these three are my inputs. Now I am doing for T1. 0, 1, 2, 3, 4, 5, 6, 7. T1 I am doing. Okay. So my T1 is 1 for alternate cases. Okay. 0, 1. 1, 2, 3. Okay. 4, 5, 6, 7. Okay. So for alternative cases, my T2 is 1. So here I can do one pair. What is my T1? T1 will be Q naught only. Okay. T1 will be my Q naught. Now I am doing for T naught. Okay, so for this case, all are 1. If all are 1 in K-map, if you see all are 1, that means the entire T naught will be as a 1, because all the variables are 1. That means if T naught is 1 only. Okay, so in K-map, if you fill the entire K-map by 1, that the output will be 1 only in this case. Okay, so I got the 3 relationship. Okay, one is T2 is equal to T1 T naught, T1 is equal to T2 is equal to Q1 Q naught, T1 is equal to Q naught, and the T naught is equal to 1. Okay, now I am drawing the model counter. Okay, so you need the 3 T flip flop. Okay, T2, T1, T naught. Okay, synchronous counter I am designing, so only one clock pulse will apply. Okay, for each. Right? So we have the Q2, Q2 prime, Q1, Q1 prime, Q0, Q0 prime. Okay. So what is your T2? T2 is the AND operation between Q1 and Q0. So I am taking variable AND operation between Q1 and Q0. This is your T2. Okay. T1 is the Q0 will directly come to the T1. Okay. So T1 will directly. This is T0. Okay. T0 will directly come to the Q0 will directly come to the T1. Okay, and the T0 is the 1. So I am connecting VCC with the T0. Okay, T0 is 1. I am connecting T0 with the VCC, and T1 is the Q0. So the Q0 is coming to the T1. Okay, and T2 is the AND operation between Q1 and Q2. Q1 and Q2 doing the AND operation, that is connecting to the T2. Okay, so T2, T1, T1. Here we will get Q2, Q1 and Q0. Okay, so that depends on the output, and past output is directly connected to the input for getting the output, present output. You can see here, right? So this is about the modded up counter using the T flip flop, right? So next class I will discuss about the how can you design the random counter, or if you have the if you want to design the mod 7 counter using T flip flop. This I will discuss on the next class. Thank you.